So in this video we're going to discuss the alternating series test, which is also known as the Leibniz test. Now this is a bunch of criteria, free criteria, which if an infinite alternating series obeys those free criteria, then you can say that that series converges. So we'll firstly state the criteria and then we'll spend the rest of the video trying to understand why it's true. So let's start by writing out our alternating series. So if we have sum from I is equal to 1 to infinity, and now an alternating series is something of the form minus 1 to the power of I plus 1 times AI. And in fact, the first criteria here of this test is going to be that all of these AIs need to be greater than or equal to 0, i.e. it needs to be a true alternating series. So each of the terms of the series is only going to be able to be negative if this bit is negative. And that's going to mean that it truly alternates between positive and negative terms. So just writing out a few of the first terms then. So for 1, that minus 1 is squared, so 1 is going to be a positive term. For 2, we've got minus 1 cubed, so that's going to be a negative term, so it's going to be minus a2, and so on. The next one's going to be positive, so all the even ones are going to be positive, all the odd ones are going to be positive, and all the even ones are going to be negative. So it will alternate between being positive and negative, the terms here. Therefore, it is a true alternating series. That's the definition of an alternating series. That's actually one of the criteria for this test. So it's a very simple criterion. So now let's write down the other two criteria for this to actually converge. So the second criteria is about these AI terms. So remember, these are all non-negative. And the second criteria is that they must be monotonically decreasing, which means that the terms of the overall alternating series are decreasing in size. They might be flipping in sign, so they might be flipping on the number line from the right of 0 to the left of 0 to the right, etc. But overall, the size of them is getting smaller and smaller. So for all I is an element of the natural numbers, AI plus 1 must be less than or equal to AI. So if we look at these two, this one is going to have a smaller size than this one. Then if you look at these two, this one's going to have a smaller size than this one. These two, this one's going to be smaller than this one in size. This one's going to be smaller in this one. Ignoring the signs, just looking at their size, which is what this criteria here says. So to put this in words, the sequence of the AIs needs to be a monotonically decreasing sequence. So that's criterion number 2. And then the third criterion is actually very simple as well. Is one that for any series to converge, we know this has to be true anyway. So something we know for any series to converge. So if you have a general, and I'm not going to write this there, but an aside up here, if you have a general infinite series, I is equal to 1 to infinity, of AI, then one of the criteria for it to converge is that these things the terms of the series must converge to 0. In particular, that the limit as I approaches infinity of the absolute value of the AIs must equal 0. And indeed, you could get rid of that absolute value. The limit of the terms of the sequence must go to 0. And indeed, that's what we're going to put here, that the limit of the AIs must equal 0. So the limit as I approaches infinity of the AIs must equal 0. And this fact here, which has been put in as the third criterion of our test, this comes immediately from just looking at the Koshi Criterion for convergence of an infinite series, which comes from the Koshi criteria for convergence of that infinite sequence of partial sums. So these three criteria then, if you have an alternating series that obeys these three criteria, you can immediately conclude that that series converges. That's what the alternating series test or the Leibniz test says. And now what we'll do is understand why it's true. So we're going to use the Koshi criterion for convergence of an infinite series then. Just going to move this up to create some more space. So remember that when we talk about convergence of an infinite series, what we're really talking about is the convergence of the sequence of partial sums. So we're thinking about this infinite sequence, S1, S2, and on it goes Sn, where all of these things, the Si's, or actually I'll continue calling them the Sn's, these are the partial sums of this series, though they're the sum from I is equal to 1 to n of the terms of the series that you're looking at. So S1 is just going to be A1, S2 will be A1 plus A2, S3 will be A1 plus A2 plus A3, all the way up to Sn being A1 plus A2 plus A3, all the way up to An, which is what's written here. And then this sequence will go on forever, the sequence of partial sums, and if that converges to a limit, that's the answer as to what the infinite series converges to. Now, in order for that infinite sequence to converge, we know that in the real numbers, convergent sequences and Cauchy sequences are one and the same. In order for a sequence to be convergent, it must be Cauchy, and if a sequence is Cauchy, it is convergent. So what we can do is we can look at what is necessary in order for this sequence to be Cauchy, and what does that tell us about, in terms of sums of the terms of the series, and that gives you the Cauchy criterion for a series to converge. So the Cauchy sequence criteria says that the terms of the sequence must get and stay indefinitely close to one another. And the way that that is captured in writing is that for all epsilon greater than 0, there must exist some big N is an element of the natural numbers, so some point in the sequence where for all points beyond there, if you pick two terms of the sequence beyond there, so two little n1 and little n2 that are greater than big N, if you look at the difference between those terms of the sequence, so Sn2 minus Sn1, that is going to be less than epsilon. You must be able to do that for all epsilon. You must be able to find a point in the sequence where it's true that the difference between the terms of the sequence are all that close, no matter which two you pick that are beyond that big N. Now, in terms of what this means for sequences of partial sums, well, one of the n1 and the n2 is going to be the larger of the two. So let's assume that n2 is the bigger one, that we label n2 the bigger one. So then if we think about what the difference between Sn1 and Sn2 is going to be equal to, well, that's just going to be the absolute value of the sum from I is equal to n1 plus 1 to n2 of the terms of the series. Because if you think about what Sn2 is equal to, it's equal to A1 plus A2 plus all the way up to An2. And then if you think about what Sn1 is, it's A1 plus A2 plus all the way up to some An1. And we're assuming N2 is bigger than N1, so it's stopping before this one. So when we subtract this one from this one, we're subtracting off all of those terms. So An1 will be somewhere up here in this sum that's making up Sn2. And so you're just going to end up with those terms that were beyond there. So the terms that were added on extra to make this larger partial sum Sn2. And that's what we've got here. So we've got all the terms from n1 plus 1, which is this next term on, all the way up to n2. And we're now saying that must get indefinitely small. And if we can prove that that's true about our infinite series, then our infinite sequence of partial sums will be a Cauchy sequence, and therefore will converge, and therefore the infinite series will converge. So what we now want to show is that if we have our alternating series here that obeys these three criteria, that this is going to follow. We want to be able to get to this from this. So let's move this down here. So we now have our infinite alternating series here. So minus 1 to the power of I plus 1 ai from I is equal to 1 to infinity. And we want to show that it's going to obey this. So we want to show that for all epsilon greater than 0, this is true. So we need to assume epsilon is greater than 0. This is for all introduction, if you're a fan of predicate logic. So assume epsilon is greater than 0, and then derive that this thing is true. Derive that there exists a big N is an element of the natural numbers. So now, existential introduction, we need to find such a big N. We need to show that this exists for a general epsilon, such that this is true. So how are we going to do this? Well, we're going to look at what the difference of partial sums is going to be for our alternating series, and it turns out that this is going to be extremely beautiful in the case that we have an alternating series that obeys those criteria. In particular, that monotonically decreasing criteria is the most important one. In that case, we can say a lot about this. So let's think about the difference between two partial sums of this. So we'll take n2 greater than or equal to, in fact, strictly greater than. We don't want greater than or equal to. So we've got some n2 that is greater than n1, and we want to think about what is Sn2 minus Sn1 in the case of this. And we're going to split it into two cases. We're going to split it into the case, firstly, where n1 is even, and then we'll look at the case where n1 is odd. Now, let's just write out a bit of the series again. So we have, remember, a1 minus a2 plus a3 minus a4. So remember, all the even terms are the negative ones, and the odd terms are the positive ones. So if we're subtracting off Sn1 and n1 is even, then the first thing along in this, the an1 plus 1, is going to be an odd term. So this is going to be all the way up to an2. But this is going to be an odd term in this case. So it's going to have it's going to be a positive term. So this is going to be an1 plus 1, and then you're going to have minus an1 plus 2, and then plus an1 plus 3, and then it will go on. And actually, this was slightly incorrect because I don't know. I didn't make any assumptions about whether n2 was odd or even, so I don't know whether that's a positive term or a negative term, but it doesn't matter. It can be either. Now, here's the clever thing. If we look at what this value is going to be equal to, just group some things together here. So group this together as so. So an1 plus 1 minus an1 plus 2, group those two together. Then group together an1 plus 3 minus an1 plus 4, etc. So group them together as pairs. Now, why is this an interesting thing to do? Well, think about what this is going to be equal to. Because of the monotonically decreasing property that this one was smaller size than this one, you can conclude that this is something greater than 0 because this one is bigger than this one. So you're subtracting off something that's smaller. So this is something that's greater than 0. It might be tiny. In fact, it might even be equal to 0 because, remember, in the monotonically decreasing criteria, it was that the next one along was either less than or it was the same as. It didn't necessarily have to step down, but it could have been the same as. So each of these things that we've got here is going to be greater than or equal to 0. And it's the same for this one along here. This is greater than or equal to this one. So when you subtract this off, you're going to end up with something that's either 0 or it's positive. It's never going to be negative. And it goes on. Now, either you have in total an even number of terms in this difference of the partial sums, and that will happen in the case that n2 was even as well, or you'll have an odd number of terms, in which case there'll be one right at the end that's unpaired. So if you had an odd number of terms, so if n2 was odd, then you'll have the final one, which will be an2. But in the case that n2 is odd, that one will have a plus in front of it, so again it will be positive. So this total sum of all of them is always going to be positive. In the case that n2 was even, you'd have all of them being paired up, and all the pairs would overall be positive. In the case that n2 is odd, the final thing that you're adding on there will also be positive. So overall, this entire thing is going to be non-negative. So what we've overall managed to conclude there is Sn2 minus Sn1 is greater than or equal to 0. Now we can conclude something else about Sn2 minus Sn1. We can bound it above as well. So we're going to put another inequality here, and this is how we're going to do that. So Sn2 minus Sn1, let's write it out again. It's equal to, and we're still making the assumption at the moment that m1 is even, so that the first term we've got here is a positive term. So it's going to be an1 plus 1 minus an1 plus 2 plus an1 plus 3, etc. onwards. This time, the way we're going to pair them up is like so. So we're going to leave the first term out, and then we're going to suck the minus out, and then we're going to pair them up like so. So an1 plus 2 minus an1 plus 3. So that we've taken the minus out the front. This one has now become positive inside the brackets, and this one has therefore had to become negative because it would cancel with that minus there. And then you go on, so the next thing along would be, oh, whoops. So again, you need to suck a minus out the brackets. So the next term along would be an1 plus 4, and that would be a minus term. So we're again going to take the minus out of the brackets, and we'll have an1 plus 4, and then minus an1 plus 5. Now an1 plus 5 would have been a positive term, but because it's now got this minus outside at the front of the bracket, it's going to become a negative term. And then either you will have a odd number of terms in total, in which case all of these ones afterwards will be in brackets, or you'll have an even number of terms, in which case that final term would have been minus anyway. So my point here is that you're going to have an1 plus 1 minus a huge number of things that are positive. So let's examine this in more detail. So if we look at all these things inside the brackets, because this one is greater in size than this one because of the monotonically decreasing property, this is some positive value that you're then subtracting off. The same holds true here. All of these things inside the brackets you're going to be subtracting are going to be positive values. Therefore, you've got this thing minus a whole bunch of things. And as I was just saying before, if overall the number of terms you've got is odd because the n2 was odd, that means that everything's going to be in brackets like this. After this one, this is going to be the only lone term, which is fine, and then all the things after are going to be in brackets, and they're going to be subtracting off positive values. If, on the other hand, you've got an even number of terms, then the final term along here, that an2, that is going to be on its own, not paired with anything, but it's okay because it's going to have a minus sign out the front, so it's still going to be one of these examples where you're subtracting something off. So you're always, everything that you're adding on after this is going to be actually subtracting off something. And that means that we can say that this sum is less than or equal to this thing, because it's this thing minus all of these other things. So we can now put that this is less than or equal to an1 plus 1. Taking this inequality a little bit further, what we can do is say that the absolute value of the size of the difference between the partial sums, Sn2 minus Sn1, is going to be greater than or equal to 0 and less than or equal to an1 1 plus 1. And that's going to be really crucial because we're trying to prove that we can make these indefinitely small and keep them indefinitely small. So having information about how big these are is going to be very helpful. So we're going to use this in a moment. Firstly, let's just consider the other case where n1 is odd now. So n1 is odd. And again, we're thinking about the difference of the partial sums sn2 minus sn1. This is going to equal, now n1 plus 1 is going to have a negative in front of it because it's going to be even, given that n1 is odd. And you'll have plus an1 plus 2 minus an1 plus 3, etc. Now, all you have to do is multiply both sides by minus 1 to get that sn1 minus sn2 is equal to this, an1 plus 1 minus an1 plus 2, an1 plus 2 plus an1 plus 3, so on. And then you can apply the exact same arguments that we've done above to say that sn1 minus sn2 is going to be greater than or equal to 0 and less than or equal to an1 plus 1. Those exact same arguments that we've done above. It's just this time we've swapped these round by sucking that minus 1 out of everything. But we can rectify that. Of course, we're interested in sn2 minus sn1, but actually what we're interested in is the absolute value of that difference. And of course, what we can now say is that the absolute value of sn1 minus sn2 is greater than or equal to 0 and less than or equal to an1 plus 1. And of course, this thing is equal to it the other way around, sn2 minus sn1, because multiplying by minus 1 makes no difference to the absolute value. So overall, what I've just argued there very quickly is that even in that other case where n1 was odd, this inequality that we've discovered still holds true. So the difference between these partial sums is still bounded above by this and below by 0. So what we have shown overall is that all these differences of partial sums are less than or equal to the first term in that sum that makes the difference. So in that sum of terms that makes this difference. And given that we know that these terms are going to 0 by the third criterion of our alternating series test, together those things are going to allow us to say that this Koshi criterion is fulfilled. So where are we going to continue? So we've assumed epsilon is greater than 0, and we now want to show that we can find a big N such that this is true. So I'm just trying to decide where to go. I think this is going to be the greatest place. So let's write down what we've discovered then now. So we have shown that for n2 is greater than n1, the difference between them, so the difference between the partial sums, sn2 minus sn1, is less than or equal to that first term, so that an1 plus 1. So remember, sn2 minus sn1 is equal to an1 plus 1 plus, this is a little bad because I don't know whether that's got a plus or a minus in front of it. I shouldn't have actually written this. It doesn't matter. So it might have a plus or a minus in front of it, but it is less than or equal to the size of that first term, which is an1 plus 1, because that doesn't have the minus 1, the plus 1 or the minus 1 bit. It's just the size bit. Now, we also know that the limit as n approaches infinity of the an's is equal to 0. So that means that these an's, they get indefinitely small. They get and stay indefinitely small. So this means that for all epsilon greater than 0, there exists a big N is an element of the natural numbers such that for all little n greater than or equal to big N, the size of these terms, so we could put absolute value of an, but we don't need to because they're all positive. So we can just put an is less than epsilon. So no matter how small you want, you can find a point in this sequence of these terms where for that point and for all the points afterwards, they are smaller than that epsilon. And now I say that we can fulfill the Koshi criterion because we've assumed epsilon is greater than 0, and we now want to find a big N that will mean that if you pick any two n1 and n2s and look at the difference between those partial sums, that it's going to be less than epsilon. Well, because I know that it's going to be less than this term, if I just make n1, or if I make n equal to the n that I need here, then all of those terms are going to be less than epsilon, and I know that these things in turn are all less than the terms. So I'll go over here. So in order to do the Koshi proof, I'll just copy it out. So we've assumed epsilon greater than 0, and we now want to find that big N. So I am saying just whatever epsilon you have that you need to do to fulfill the Koshi criterion for the infinite series, just plug that epsilon into this limit definition here. We know that this limit is true, so we know that if you give me any epsilon, I can find you a big N. So take that big N. Drawing out a picture of this series, so we've got, of this sequence, we've got A1, A2, and it goes on. So we're now extracting a big N here. We're saying we've used this epsilon, we've obtained this big N, and now for all the terms of the sequence beyond there, they are all less than that epsilon. So for all little n is greater than or equal to this big N, the terms of the series are going to be less than epsilon. Now, if you were to take an n1 and n2 that are greater than or equal to that big N, and we'll again assume that n2 is the bigger of the two, and you were to look at the difference between their partial sums, so Sn2 minus Sn1, that is going to be less than the An1 plus 1, that first term. But because n1 is greater than or equal to n, it satisfies this. So we know that this term is one of these terms, so it's going to be less than epsilon. So by transitivity, this is now less than epsilon, which is exactly what we needed to show. We needed to show that given an epsilon, we could find big N such that this was true for all n1 and n2 greater than that big N. And I said that I have done that because I've used this. So that is overall the explanation then of how those three criteria mean that this alternating series is going to converge. Overall, they mean that the Koshi criterion for the convergence of a series is going to apply for these alternating series. So I hope that's been clear. Thank you for watching.